All right, in this problem, we have a particle that's going along this path defined by y equals 0.5 x squared. Okay. We also know that its velocity in the x direction is defined by 5 times t, where t is time in seconds. What we want to do is we want to figure out the position and magnitude of the acceleration when t equals 1 second. All right, so we will start with the fact that the velocity is equal to the time derivative of position. We'll do this in the x direction since that is what we have the relationship to. We have the velocity in the x direction as a function of t. So essentially I'm going to integrate that in order to get a relationship between position and time. Okay, I know my initial conditions. I do an indefinite integral, and I get the following: x equals 2.5 times t squared. So that is the x position as a function of time. Right? The y position is given by this equation right here. So I just plug in what I know about x into my equation for my path. So I take that 2.5 t squared and I throw it into where x is, and I'm left with this equation, which is 3.125 t to the fourth for the y equation. Okay, so now I've got x as a function of t and y as a function of t. So I can just plug in 1 second for both x and y and figure out its position at 1 second. That's the first part of the problem. Okay, so again, just taking what I know about the velocity, I integrated it so I could find the x position as a function of time. Then knowing the relationship between x and y, I can find the y position as a function of time. Then I plug in 1 second, figure out my x and y. All right, now moving to the next, we have to do something a little bit different. Okay, so we're going to start with our path equation. Okay, now I need to move to acceleration. Okay, so we're going to do something. We're going to actually differentiate this equation with respect to time, because this is essentially a position equation. I'm going to differentiate it twice so I can figure out acceleration. Now, keep in mind I'm differentiating with respect to time, and time is not in this equation anywhere. So here's how I do that. I get this. Y, okay, the time derivative of y is by definition y dot, right? dy dt, that's how we write that, y dot. And that's a shorthand for time derivative of y. That's where we get that. Okay. 0.5 x squared, if I'm going to take a time derivative of that, okay, 0.5 is constant, so if I take a time derivative of that, it goes away. So we're going to pull that out. Okay, it's a constant, I'll pull it out. Okay. X squared is the same as x times x. I'm going to use a chain rule on that, which is effectively x times x dot plus x dot times x, right? Time derivative of one times the other, then the other times time derivative of first, right? That's how we do that. So again, we have essentially, if I have that, I go x dot dx dt times x plus x times x dot, or 2x dot x. So I have 2x dot x times 0.5, and I'm left with x times x dot. Okay, I have to do it again now. Okay, so maybe it'll go better this time. I'm going to take a second time derivative. Of course, the time derivative of y dot is just y double dot. The time derivative of x dot, I have to do that chain rule again. So I take the derivative of the first, which is x dot, times the second, which is x dot. Therefore, I have x dot squared, plus the first times the derivative of the second. The first is x. The time derivative of x dot is x double dot. That's where this equation comes from. Now, what we're looking for here is acceleration, which is, I have an x component and a y component, x double dot and y double dot. Okay, so I could rewrite this like this, right? Instead of y double dot, I have the acceleration in the y direction. Instead of x dot, I have the velocity in the x direction, x a in the x direction. Okay, now I know from this equation that was given to us, I know the velocity is 5 seconds, or I'm sorry, when at 1 second is 5 feet per second. So I know Vx here in this equation. Ax is the time derivative of Vx. That one's pretty simple, right? A equals dv dt. The time derivative of 5t is simply just 5. So I know the acceleration in the x direction. Therefore, I can solve this equation for ay by plugging in 5 for Vx, x, which is 2.5 calculated earlier, and ax, which is 5 feet per second squared. And I get 37.5. Magnitude of this is just square root of the sum of the squares. The trick on this, again, is what we did up top here, okay? Where we take a time derivative of an equation that doesn't have time in it. So we throw in these dots, we do some chain rules, and we work through it that way. And with practice, that'll become easier to do, okay? Once you get two derivatives down, then you can plug in things that you know to solve for the acceleration in the x as well as the acceleration in the y.